For our research project, we covered a performance review of computing Dijkstra's shortest path algorithm using serial and parallel implementations. Our team consists of Kevin Barnett, James Bryant, Christopher Summers, and Chase Kosek. To introduce this problem, this research paper that we found was based on the paper Dijkstra's shortest path algorithm serial and parallel execution performance analysis conducted by the University of Sarajevo. This research was conducted in order to examine the parallelization capabilities of one of the most well-known shortest path algorithms, the Dijkstra's algorithm. Real-world applications for this algorithm. Dijkstra's algorithm has many real-world applications such as traffic engineering and internet protocol networks, intelligent transportation systems, and so on and so forth. Currently, most serial shortest path problems have reached the time limitation, leaving parallelization as the clear next step. Related work. As mentioned previously, this paper is based on the paper Dijkstra's shortest path algorithm serial and parallel execution performance analysis. In their findings, the team found that their serial and parallel implementations performed almost exactly the same from less than 3,000 nodes, and they were able to achieve the maximum speed up of 10% with the parallelization. The team also found better GPU performance than CPU performance. However, that testing was left out of our data collection. Conclusions for related work. The research team made the following conclusions about the major issues of parallelizing Dijkstra's: limited explicit parallelism and the need for excessive synchronization. These are a result of Dijkstra's algorithm's reliance on a priority queue, making parallel evaluation non-efficient or less efficient than serial. The team, however, highlighted some areas for further work. Further work. Insufficient code. The team compared many versions of Dijkstra's algorithm and created implementations in Python, C++ before deciding to choose C for the project. The issue of at a similar number of nodes, there could be more time spent on parallelization calculations than in serial execution. This is an inherent issue with parallelizing Dijkstra's algorithm. Utilizing shared memory, avoiding branches, choosing appropriate data structures, and designing the parallel algorithm correctly. These final suggestions were taken into consideration and used by the team. Proposed research. The proposed research by the group was to develop both a serial and parallel implementation of Dijkstra's algorithm in C. The performances of these two were then to be tested on the 4 machine configurations available to the team members. In order to test the algorithm's performances comparatively and hopefully confirm or deny the research team's findings of 10% speed up and noticeable improvement past 3,000 nodes. These were the following configurations that were used in the experiment.
We have a Python script that we use to generate the graphs that we would use in our Dijkstra's algorithms. The Python script would take the size of the graph and the minimum and maximum number of node connections, and would create a 2D array that represented the distance from each node to each other node. So for example, at graph 0, 0, this would always return 0, because we're talking about node 0's connections, and the distance from node 0 to node 0, and since that node is itself, it will always be 0. So this graph is initially filled with zeros, where the two indices are the same, and the rest is filled with the maximum value of an integer in C. Next, we use the random library to choose a random number between the minimum and maximum number of neighbors. And then we used a while loop to repeatedly assign new neighbors where there weren't any neighbors. It would assign a distance from 1 to 10, and then at the end of this, the graph would be put into a file that would be read by our C program for Dijkstra's algorithm. We generated one graph of each size, then we would use the same graph for each of our 4 configurations and each of our algorithms so that we could accurately assess the speeds for both versions of the algorithm. This is an example of what that Python program might make. This is an example for 5 nodes. You can see that the diagonal is all zeros. We have some numbers between 1 and 10 that represent the distances between the nodes. And we also have the maximum value of an integer in C, and these are nodes that are not connected to each other. So for the serial version of Dijkstra's algorithm, we start with a source node, and we would set the distance of that node to 0. And then we would initialize a shortest path array, and this is all going to start with a maximum integer value, except for the source node, which will be 0. And then we would find the least cost connected neighbor, so the neighbor that is currently the shortest distance from the source and that hasn't been visited. And we would add that node to the shortest path array and update the minimum distance to each of our unvisited nodes, and then we'll repeat that process of finding the least cost connected neighbor and updating the unvisited nodes until all the nodes have been visited. And at the end of that, you should have the shortest path from the source to each of the other nodes. This is how we did our serial implementation. We made a C function called Dijkstra serial, and this would take a graph that was a 2D array that we had generated with the Python script, and it would take an integer that represents the index of the source node. And this graph would have all the connections and their weights to each other node. And we would use a visited array to keep track of which nodes had been visited or had not been visited, so that we would be able to implement the algorithm. After this is ended, the main function would write the return shortest distance array to an input.txt file, which has 3 different columns. The first column is the node position. The second column is the shortest path found using our serial algorithm, and the third column is the shortest path found using our parallel algorithm. So our parallel implementation functions really similarly to the serial implementation. We also initialize a visited and shortest distance array, but what's different in our parallel implementation is that each thread that's created will divide up the nodes among them. They should each get an equal subset of the nodes, and the parts of this algorithm that are able to be split up and not happen in a certain order are done in a parallel way. So within each thread, it's going to find a minimum distance, the node with the minimum distance that it's responsible for, that each thread is responsible for. And then the threads will converge and find the true minimum node, and it will use that for the algorithm. And then each thread will also update the minimum distance for all of its unvisited nodes, and then it will converge again. And this is going to continue to repeat just like before until all of the nodes have been visited and the shortest distance array is returned. So here's one example of Dijkstra's algorithm that uses the input.txt that we saw earlier. And so we started out with node 0 as our source node, and we first chose the node that has a distance from 1 from node 0, and we highlighted it green to show that it had been visited, and we updated its neighbors, which now has a distance of 9. We chose the node with a distance from 4, highlighted it green to show that it's been visited, and updated its neighbors to show that one of its neighbors now has a minimum distance of 7. We chose that neighbor with a minimum distance of 7, highlighted it green, and it didn't have any neighbors to update, and then we visited our final node. We now have visited all of our nodes and we're able to return that. And here's an example of our file output. The first column represents the position of the node, or the index of the node in the graph that we started with. The second column is the shortest distance found from the source node using our serial algorithm, and the third and final column is the distance found from the source node using our parallel algorithm. As you can see, since our second and third columns are both the same, we can say that the algorithms return the same thing and are functioning properly.
Alright, now we're going to talk about the evaluation of our results. Here you can see the graphs for configuration 1, which was statistically one of the middle of the road configurations that we had. As you can see from the graph on the left, the serial time for the serial execution time is far faster than the parallel time, and that can be seen in the speed up chart over on the right as well. In configuration 2, it's more of the same, is that the parallel is much slower than the serial. The speed up on the right also shows the same thing. Here, now next we'll go to configuration 3, and the serial is faster for the most part than the parallel, all the way up to 10,000 nodes. And that can also be seen in the speed up over on the side. And finally, with configuration 4, the parallel is much slower than the serial. For each of these configurations, 4 threads were used for the parallelization, except for configuration 4. Configuration 4 used 6 threads. And the reason that we believe that the parallel is much slower than the serial is that a lot of the execution for Dijkstra's algorithm has to be done in order. Like, it waits, it relies on previous answers and the order of operation of the answers, and we think that just the creation of the threads to just have to sit there and wait most of the time keeps it from being actually faster, in our case, than the serial execution time. We also did this. We also checked the number of connections versus the time taken, the number of connections that each node has, and in these charts, you can see that, again, the serial was much faster than the parallel for configuration 1, which is on the left, and also in configuration 3, which is on the right. Configuration 3 was a little closer for some of the connections, but for the most part was much slower. Each of these test files had 5,000 nodes, so there was some standardization in there, and they had a range of connections that they could have between that were in increments of 5 all the way up to 100, starting from 10. Here we also have all of the serial performances charted for all the configurations on a similar chart, so we can really get an idea of which one of the configurations performed the best. And as you can see, configuration 4, which was the configuration with the i9 and the 12 threaded or the 12 core processor, was by far the best, followed by configuration 2, and then 3, and then 1 were the best for the serial execution times. And finally, we find on the parallel execution times that configuration 3 actually ended up being the fastest for the majority of the time. It's set for around 9,500 and 10,000 nodes per chart. And then configuration 2 and 4, despite having huge disparities in their processors, were about the same. And then configuration 1 was also just the worst at parallelizing the algorithm.
Okay, so on to our conclusions. The experiment results were not quite what we expected. We more so expected a parallelization to increase the speeds, as the first research team found and as the research paper presented. They only achieved speed ups of about 10%, which is not too significant, but we still expected to see some speed up, especially with above 3,000 nodes, which is what they reported. But due to holding of threads and parallelization and the lack of areas to parallelize with the Dijkstra algorithm, we actually did not see the speed up at all in ours. And we may have, if we continued on to see the higher number of nodes, we may have eventually seen the speed ups, but we did not. And I think the max speed up we achieved was 0.8, which is 20% slower than our normal serial version. Compared to the related work, our algorithm ran about 300 times faster, with both of our algorithms running 5,000 nodes in nearly 1.5 seconds, while theirs had about an average speed of 400 seconds for their 5,000 nodes. So one issue that could be to blame would be that they just used very slow algorithms, both serial and parallel-wise. And also theirs seemed to grow exponentially for the amount of time it took. So we would assume that it would only take longer up to 10,000 nodes, where ours, I think the longest for our 10,000 nodes was about 5 seconds. So in parallel or serial, with parallel being slower for ours. So using an inefficient serial implementation could also be why the other team found their speed ups and why we did not. So our work versus their work. Here you can see our worst configuration, which was configuration 1. It's parallel and serial outputs, and then you can see their best configurations outputs. Here you can see how much faster ours seemed to be. With 10,000 nodes, we still only reach about a little over 5 seconds or 4 seconds, while theirs was reaching about 340 seconds or so. And their serial was still only at about 300 seconds, but our serial was well below that at a peak of about 2.5 for 10,000 nodes. So double the node size and 2.5 seconds instead of 300 seconds. So I think that would be a big reason why our work didn't end up the way we expected it, whether that is us having an effective serial version of the Dijkstra's algorithm or theirs just being very ineffective. However, we don't think that just their hardware being worse than ours would be to blame for this. So that would be our findings. And for speedups through the 500 to 10,000 nodes show steady growth in the amount of speed up. This could also mean that at a larger size, the parallel could eventually surpass the serial speeds. However, the top speedups achieved in our testing was 0.8, which is 20% slower than the serial still. So basically, we may have eventually achieved speed up with our parallel version had we gone much over 10,000 nodes. However, the Dijkstra's algorithm just may not be worth parallelizing, especially if you need to be at node sizes that large to see the effects of the parallelization. This could also be in part due to our version of parallelizing the Dijkstras, as we had to wait with a lot of the threads or wait for one thread to finish, which effectively made parts of our Dijkstra's parallelization still serial. This also meant that we had to hold up all the other threads at a lot of points just because of the way Dijkstra's works in finding the shortest path and shortest connections to all the nodes. So overall, though, Dijkstra's algorithm can be parallelized. We found that our speeds were 20% slower about for the parallelized version and much slower at the lower node counts than our parallel, or for our serial was much faster than our parallel. So overall, unless you're dealing with very large data sizes, we would not recommend attempting to parallelize the Dijkstra's algorithm for any kind of node searching. And thank you all for your time, and we hope you enjoyed the presentation.